At 3:17 a.m., a sensor nearly 2 miles beneath the Pacific Ocean detected something it was never built to find. Not motion, not pressure, not sound. Heat, a sharp surge. Clean, focused, wrong. The system flagged it as a malfunction. It reset automatically, recalibrated, scanned again. The numbers climbed higher. Far above, the ocean remained indifferent. Wind skimmed across dark water. Cargo ships cut steady lines through the night. Satellites traced their silent orbits, blind to what was unfolding below. Down in the cold abyss, where sunlight has never reached and temperatures hover just above freezing, the seafloor was warming. Not gradually, not subtly, rising. Within 6 minutes, 3 additional monitoring stations scattered across hundreds of miles transmitted identical readings. Independent networks, separate data streams. No shared circuitry, no shared software. All reporting the same anomaly, all showing acceleration. There were no tremors, no volcanic plumes, no chemical signatures of eruption, just a thermal spike spreading through rock and sediment older than civilization. Engineers reran diagnostics, oceanographers cross-checked baselines. Algorithms searched for precedent. There was none, because this wasn't noise. It was a signal, and it was getting stronger. The Pacific Ocean is not empty. It is wired. Across its floor, in trenches deeper than mountains are tall, thousands of instruments stand watch. Pressure gauges bolted into tectonic fractures. Hydrophones tuned to vibrations inside stone. Thermal probes buried in sediment, measuring gradients too small for human skin to feel, yet large enough to reveal movement inside the planet. They exist for one purpose: warning. They listen for earthquakes before they strike. They register volcanic unrest before magma breaks the surface. They detect submarine landslides before the water above them begins to rise. They track the slow collision of continents, movements so gradual they seem motionless, yet powerful enough to reshape the world. They record everything. Most nights their transmissions are uneventful, graphs drift in narrow bands. Numbers fluctuate within safe margins. Algorithms scan, confirm, archive, a mechanical calm, predictable, routine. But on this night, routine ended. In the Central Pacific, a cluster of monitoring stations began sending readings that did not resemble any known geological signature. At depths, where seawater typically hovers just above freezing, temperatures were climbing, not gradually, rapidly. The increase outpaced anything oceanographers had documented outside an active undersea eruption. And eruptions are unmistakable. They fracture crust, they release gas plumes, they generate seismic noise that echoes through the planet. None of those signals appeared. No tremor signatures rippled across seismic arrays. No shock waves registered in hydroacoustic sensors. No mineral plumes clouded the water column. Only heat. Researchers watching the live data feeds assumed malfunction. Instruments fail, salt water corrodes seals, electronics drift, circuits misfire. False readings happen. They initiated diagnostics. Internal checks showed no hardware faults. Voltage levels were stable. Calibration logs were intact. Error flags were absent. They compared the readings with satellite thermal imaging, scanning the ocean surface for corresponding anomalies. If heat were rising from below, subtle changes might appear above. The satellites saw nothing. They pulled seismic records from regional networks. If magma were intruding upward, rock would fracture. Even microscopic shifts would leave signatures. The logs were silent. They checked adjacent stations outside the anomaly zone, expecting normal baselines. Those stations were no longer normal. Their temperatures were rising too, slowly at first, then faster. That was the moment routine analysis turned into focused attention. Because isolated errors are common, instrument clusters can fail, local interference can distort signals, but independent stations agreeing with one another across distance, across systems, across infrastructure rarely happens by accident. The anomaly was no longer a point. It was becoming a pattern, and patterns in geophysics mean process. Somewhere beneath miles of water and layers of ancient crust, energy was moving. The first hypothesis was the simplest: underwater magma movement. Beneath Earth's crust stretches the mantle, a colossal layer of dense rock flowing slowly under immense heat. It is powered by forces older than continents, radioactive decay, primordial energy left from the planet's birth. In certain regions, molten material rises through weak zones in the crust, forming volcanic arcs and hydrothermal systems along the ocean floor. If magma were ascending beneath this section of the Pacific, the temperature rise would make sense. But magma is never subtle. It cracks stone as it forces its way upward. It releases dissolved gases. It sends vibrations through surrounding rock, signals so distinct they can be detected by seismic stations thousands of miles away. No such signals appeared. The crust was quiet. The sensors heard nothing. The rock was not breaking. The second theory focused on tectonic stress. The Pacific Basin rests on a mosaic of immense plates, continental slabs drifting slowly atop the mantle. Their motion is almost imperceptible, measured in centimeters per year, yet the pressure they generate can equal millions of tons. Where plates meet, strain accumulates. When that strain releases, the result is an earthquake. Some geophysicists propose that friction deep below the crust might be generating heat before a major rupture. A locked fault preparing to slip. A silent buildup of energy, but the instruments designed specifically to measure tectonic deformation showed no anomaly. No compression spikes, no strain acceleration, no shift in alignment. The plates were motionless. The heat was not. A third explanation entered discussion in quieter tones. A deep mantle anomaly. Far beneath the crust, hundreds of miles down, lie regions humanity cannot observe directly. Their existence is inferred from seismic waves bending through the planet's interior, revealing shapes and densities like shadows cast inside stone. Some of those shadows suggest towering structures rising from the deep mantle toward the surface, columns of hotter material moving upward over geological time. If one of those structures had shifted, if a surge of heat were traveling through an unmapped pathway, it could warm the seafloor from below without triggering immediate quakes. But that scenario implied motion on a scale rarely witnessed in real time. Something vast, something slow, something powerful enough to alter temperature across hundreds of miles of ocean floor. Then came the hydrothermal cascade theory. The Pacific seabed is scattered with vents, fractures where seawater seeps downward, heats against molten rock, and erupts back into the ocean as mineral-rich jets. These systems can exceed temperatures of molten lava, yet remain stable for decades, sometimes centuries, unless disturbed. If pressure changed in one vent field, it could destabilize another and another, a chain reaction of thermal releases stepping outward across the crust. But the data pattern did not resemble a cascade. It showed rhythm, a measured rise, a pause, another rise, not random, not chaotic, pulsing, regular, expanding, coordinated, which led to the final possibility discussed behind closed doors. Not theoretical, not simulated, not predicted. An unknown geological process, something unrecorded in the entire history of ocean observation. Something happening now. Heat beneath the ocean floor is not curiosity. It is stored force. And when force shifts inside Earth's crust, it rarely remains contained. If temperatures continue rising, the stability of submerged continental slopes could weaken. Vast shelves of compacted sediment, built over millions of years, can lose cohesion when heated. When that happens, entire sections of seabed can detach without warning, collapsing into the depths. These events do not announce themselves. No sound reaches the surface. No light marks the moment. Miles above, the ocean appears unchanged, but the water feels it. When seafloor drops, it displaces everything above it. Billions of tons of seawater surge upward, forming energy waves that radiate outward in expanding rings. In deep ocean, those waves are nearly invisible, long, low, and fast. Faster than commercial aircraft. A disturbance in the Central Pacific could send that energy racing across entire basins. Hours later, coastlines thousands of miles away would experience the result. Shores that seemed calm would begin to withdraw. Harbours would empty, then the water would return, carrying momentum gathered across an ocean. Most people would never know what triggered it. They would only see the horizon rise. And landslides are only one possibility. Heat migrating through crust can also alter pressure along ancient fault lines. Fractures that have remained locked for centuries. These boundaries hold enormous strain, restrained only by friction and rock strength. Change the temperature and you change the balance. If that balance fails, release is instantaneous. Mega earthquakes do not build gradually. They rupture. The ground convulses, structures twist, infrastructure fractures. Offshore ruptures carry an added threat. Vertical displacement. When a massive slab of seabed lifts or drops even a few feet across a broad region, it transfers that motion directly into the ocean above. The Pacific contains more water than all continents combined. Disturbances within it do not stay local. They propagate. They interact. They echo across planetary systems. Currents shift. Thermal layers reorganize. Marine migration routes change. Nutrient flows redirect. Fisheries feel it first. Weather feels it next. Ocean circulation is one of Earth's primary climate regulators. It moves heat from the equator toward the poles, stabilizing atmospheric patterns that govern rainfall, storms, and growing seasons, alter those currents, and the atmosphere responds. Storm tracks drift, rain belts relocate, dry regions expand. What begins as heat in darkness can become change in daylight. Because the deep ocean is not isolated from human life. It is connected to everything. In research centers across the world, night has no meaning. Screens glow against dark walls. Digital maps pulse with color. Data streams scroll in steady silence. Oceanographic institutes, geological observatories, university laboratories, and monitoring agencies remain linked by one shared feed of numbers arriving from the Pacific abyss. No alarms are sounding. No emergency bulletins have been released. Inside these rooms, discipline holds. Voices stay low, movements stay precise. Every action follows protocol. Yet beneath the professionalism, the air carries weight, the kind that settles when experts see something they cannot immediately explain. Analysts study live graphs as they refresh in real time. Thin lines drift upward where decades of records say they should remain level. Temperature curves bend beyond statistical margins. Timestamps update faster than expected, as if the event itself is accelerating. One researcher overlays the incoming data onto historical baselines spanning 20 years of ocean monitoring. Seasonal cycles, El Niño fluctuations, volcanic disturbances, instrument noise. Every known variable appears on the comparison grid. The new line does not align with any of them. Another analyst examines satellite altimetry, scanning for minute elevations on the ocean surface, barely perceptible bulges that can reveal pressure or heat rising from below. Pixel by pixel, frame by frame, the surface is inspected for distortion, nothing visible. A third feeds the thermal increase into predictive simulation software calibrated for submarine eruptions. The system runs thousands of modelled outcomes, testing whether known volcanic mechanics could generate the pattern. The projections return inconsistent. No eruption scenario fits. No existing template reproduces the signal. Coffee sits untouched beside keyboards. Hours pass unnoticed. The only movement is the steady flicker of numbers updating across the displays. They are watching closely. No speculation leaves these rooms. No theory is spoken without evidence. Each possibility must withstand verification, replication, and scrutiny from peers who trust data more than instinct. In science, conclusions are not declared, they are earned. But observation requires no approval. Observation is immediate. Key in, and at this moment, every instrument connected to the network is reporting the same thing. The heat beneath the Pacific seafloor is still rising, not stabilizing, not slowing, rising. For most of history, the deep ocean was unknowable. Crossed, never seen. Now we map it, wire it, measure it, and assume that means control. But Earth reveals itself in signals. And this one is rising. Heat in ancient darkness. The planet is not still, it is stirring.